You spent, I don't know, countless hours in the digital lab painstakingly trained this language model. Maybe 3.5 billion parameters, you fed it 800 billion tokens, all works. You run it on the standard benchmarks, and it's fine, good even. But nothing that screams paradigm shift. You're kind of thinking, is this really all there is? Just building a bigger parser? Then you hit that one magical switch, you crank up the test time compute, you let this recurrent block iterate, just loop, and just think longer in its own latent space. And suddenly, bam, GSF-8K, the math benchmark, it lights up like a Christmas tree. Performance jumps, like your little 3.5 billion parameter model suddenly decided it was some 50 billion parameter behemoth. The ARC challenge, open book QA, yeah, they pick up the pace too, but math. Oh, math is where this model truly, truly sings.
And what's so fascinating here is how it's doing this. It's not, babbling out intermediate steps like those traditional chain of thought models we've seen. There's no need for bespoke training data, no massive context windows needed. It's just looping in its own continuous hidden space, turning raw compute into genuinely better answers. You're really not just building a bigger parser anymore. You're kind of building a bridge between fixed parameters and, well, potentially infinite compute through reasoning.
And that is exactly what we're diving into today, this really novel approach to language models that scale by thinking in continuous space. So get ready for some serious aha moments, because we're about to unpack how this works, why it matters, and maybe what surprising hidden talents pop up when a model learns to, well, think before it speaks. Okay, so let's set the stage a bit. For a long time, the main push in LLM scaling was just about making models bigger, right? More parameters, chuck more data at it. Then came this realization that you could also scale test time computation. And the mainstream approach we've talked about before, chain of thought, that's where models literally verbalize their steps. They write it all out in the context window, like asking a student to show their work on a math problem, essentially.
Precisely. But this new approach, it offers a fundamentally different path, recurrent depth. The core idea is this novel language model architecture that scales test time computation, but it does it by implicitly reasoning in its latent space. So think of it like this. Instead of writing down every single step for us to read, the model just iterates a recurrent block internally. It unrolls to, well, arbitrary depth at test time, as they put it. It's actually quite similar, they suggest, to how humans do a substantial amount of thought before the first word of an answer is uttered. It's that deep internal processing happening in this hidden continuous space.
That internal thought, that sounds incredibly powerful. So how is this recurrent brain actually structured? Can you kind of walk us through the key parts?
Yeah, certainly. If we break down the architecture into, let's say, digestible parts, it has three main functional groups. First, there's the prelude. This uses pretty standard transformer layers to embed the initial input data into this special latent space. Then you have the core recurrent block, and this is really the heart of it. It's the central unit that loops, iteratively processing and updating its hidden state. As the researchers cleverly put it, by looping the core, we can put an indefinite amount of verses in our song, which I kind of like. And finally, there's the coda, which basically unembeds from that latent space and has the prediction head that gives you the actual output.
Okay, and it sounds like there's some really clever design choices baked in that make this whole system stable and effective, right? What are some of those crucial bits?
Absolutely. Stability at scale is, well, it's paramount. And they've put in some key elements. One is injecting that embedded input from the prelude into every single step of the recurrence. This seems to stabilize the whole process and encourages what they call path independence, which basically means, no matter where its internal thought might start wandering from, it consistently gets to the same stable, correct reasoning path.
Oh, okay.
Another critical design choice is the sandwich format of norm layers within each block. You can think of it like carefully placed guardrails. They prevent the model's internal calculations from just spiraling out of control. And that's absolutely crucial for stability when you're training these things at scale.
That sounds like a really compelling architecture.
Yeah.
So how does this theoretical brilliance actually translate into, real-world performance? What do they find?
Well, the proof, as they say, is in the pudding. And this isn't just theory. They scaled up a proof of concept model to 3.5 billion parameters trained on a hefty 800 billion tokens. And its capability, it's genuinely impressive. It dramatically improved performance on reasoning benchmarks, sometimes reaching a computation load equivalent to what you might expect from a, say, 50 billion parameter model.
Wow.
So this isn't just about bigger numbers. It feels like a fundamental shift. It proves that a smaller model can achieve bigger results by thinking smarter, not just by scaling up brute force. And just to reiterate that contrast, Unlike chain of thought, this doesn't need specialized training data. It works fine with small context windows, and it seems able to capture types of reasoning that aren't easily put into words. It's really doing some thinking, not just, babbling out intermediate steps.
That really is a significant advancement. So, okay, beyond just the impressive benchmark scores, why do you see this whole thinking in continuous space thing, this recurrent depth, as such a fundamental shift? What are the unique advantages it really unlocks?
Well, it unlocks several critical advantages, I think. Efficiency is certainly a big one. These models need less memory, both for training and for inference, compared to the traditional chain of thought models. And that's mainly because they don't need those super long context windows to write everything down. And they also perform more FLOPs per parameter. That's floating point operations, the raw calculations, which significantly cuts down on communication costs between accelerators. That's a huge deal when you're training at massive scales. It's just a more compute efficient way to get to those higher reasoning abilities. But then, on a more maybe profound level, this compute-heavy architecture with its smaller parameter count, it really sets a strong prior, sort of nudges the model towards solving problems by genuinely thinking. And by that, I mean learning meta-strategies, learning logic, abstraction, instead of just relying on memorizing answers it's seen before. It also aims to capture those facets of human reasoning that kind of defy verbalization. Things like spatial thinking, physical intuition, maybe even motor planning. When you think about reasoning in a high-dimensional vector space over many iterations of this recurrent process, it allows for this deep exploration of multiple directions at once, instead of just being stuck in linear step-by-step thinking. So it genuinely builds what you could call a third axis of scaling. It complements the traditional ways of just adding more parameters or doing longer verbalized inference.
Okay, this next part gets into some really cool practical implications. It sounds like these recurrent depth models inherently simplify some advanced LLM use cases, like they come with certain capabilities built in. What are some of these zero-shot features that just kind of work without extra training?
That's exactly right. They come with this suite of zero-shot capabilities baked in. For instance, adaptive compute at test time. The model can intelligently vary how much compute it uses for each query. It can stop iterating early if the prediction seems easy, saving resources, but then think longer when the problem is hard.
Like it knows when to try harder.
Pretty much. It's like your brain automatically deciding how much effort to put into a problem, more for the tricky stuff, less for the simple ones. And the key thing is, this happens zero shot. No specific training needed for these early exits. It just uses a simple criterion, something like the KL divergence between successive steps, which basically measures how much the model's internal thought is changing from one loop to the next. If it's not changing much, it's probably settled. And interestingly, they found the model exits earlier on, things like high school math, but takes, on average, like 3.5 steps more on moral scenarios, which makes intuitive sense, right?
Yeah, that does make sense. Very cool.
And another fascinating feature is KV cache sharing. This cuts down the memory footprint of the key value cache by sharing entries between the layers, or rather, between the iterations. Now, in non-recurrent models, getting this to work usually requires training from scratch with specific techniques. But here, the model can just share KV caches. They use this clever I-mod K method, basically reusing certain entries intelligently with minimal hit to performance. It's a huge memory saver, which could make these models much more deployable on, say, local hardware.
That is a significant memory optimization. Okay, what else comes out of the box with this approach?
Well, we also see something they call continuous chain of thought, or maybe latent coat is a better term. So instead of generating a totally random initial state for each new token it predicts, the model can warm start the current token's latent state using the final latent state from the previous token.
Ah, so it carries over some context in the last step's thinking.
Exactly. It allows the model to, as they put it, benefit from latent information encoded at the previous generation step and further improve. It's effectively building deeper computational graphs as it generates text. And they saw on tasks like philosophy, the exit distribution shakes noticeably. The model more often exits early because it's recycling compute from the previous step's thought process. And finally, there's self-speculative decoding. Recurrent depth models can generate text more efficiently without needing a whole separate draft model, which you usually need for speculative decoding and standard transformers to speed things up. This model can essentially draft the next tokens using fewer iterations, maybe a quick thought, and then verify or refine them with more iterations, reusing the states it already computed. It makes the whole drafting process inherently efficient.
Okay, wow. So we understand what it is and what it can do with these cool zero-shot features. Now, let's really dive into the fascinating, what's genuinely happening inside this model's mind as it's thinking in this latent space. It's not just some impenetrable black box, is it?
That's a great question, and surprisingly, no. We can actually get a glimpse inside. Researchers analyzed the trajectories of the model's internal states as it iterates, and what they found is that the convergence behavior, how quickly it settles, depends heavily on the context. Key parts of a question, or say the beginning of a response, are deliberated much more. The model seems to spend more internal computational effort, more loops where it's most needed. And this is where it gets really profound, I think. They observed these emergent computation patterns, things that weren't explicitly trained for, but just sort of appeared as the model scaled. For many tokens, for instance, the internal state just converges to a fixed point. It stabilizes quickly, easy stuff. But for harder questions, especially numerical ones, the state falls into these fascinating orbit patterns in the high-dimensional space. One really striking example they mentioned was seeing the model effectively rotating the number 3 on which the problem hinges for a specific math question.
Wow, rotating a number.
Yeah, it's like watching these hidden geometric dances inside the machine's mind. And they say these patterns go far beyond simple arithmetic.
That image of rotating numbers is incredibly vivid.
Wow.
Were there other surprising patterns or dynamics they saw that kind of shed light on how it operates?
Yes, definitely. They also observed what they called sliders. These are trajectories where the internal state noticeably drifts in a single direction over the iterations. The hypothesis is that the model might be using these sliders to implement some kind of mechanism, maybe to count how many iterations have passed, or perhaps to track progress through a really complex problem. It's still a bit speculative, but interesting. And despite all these complex, learned dynamics, a really crucial property called path independence emerged. Which means that even if you start the recurrence with different initial random states, they consistently lead to the same orbital patterns, the same fixed points, or the same directional drifts. It shows this remarkably consistent internal processing, regardless the exact starting point of the thought. So what does this all mean for how we understand it? Well, it gives us this unique glimpse into how the model is actually performing its computations. Unlike that discrete sequential chain of reasoning you see in verbalized chain of thought, here we observe these rich geometric patterns. It's like a new way the model is leveraging its high-dimensional space for reasoning. It really is a different kind of internal computation.
A truly different paradigm. Okay, let's ground this discussion back in some concrete results. How does this recurrent model actually stack up on benchmarks against other established models people might know?
Right, the benchmarks. So the 3.5 billion parameter recurrent model, it generally outperforms the older Pythia series and is roughly comparable to the first Olmo generation on general tasks. So, respectable. However, its true strength really shines in specific areas. It significantly surpasses all models except the latest Olmo 2 model in mathematical reasoning that's across both GSM-8K and the harder math benchmark. And on coding benchmarks, it actually beats all other general-purpose open-source models, even though, it doesn't quite match dedicated code models trained on trillions of tokens of code.
Which makes sense, right?
Totally. If the model is learning to rotate numbers internally, it's maybe developing a kind of mathematical intuition that purely verbal models might struggle with. That seems to be why GSM-8K and complex coding logic are where it really excels.
Okay, so where does the recurrent specifically give the biggest boost? Is it always better than a non-recurrent model of a similar size, or is it task-dependent?
It's definitely more pronounced on harder tasks. If we compare it directly against its non-recurrent twin-so, trained with the exact same setup, just without the looping, the recurrent model substantially outperforms on harder tasks, such as the ARC challenge set. There's a really pronounced advantage there. On simpler tasks, maybe like PsyQ, which is more about just recalling facts, the performance is much more similar. And we also saw that the gains from reasoning are especially prominent on GSM-8K. The 180 billion parameter recurrent model they mentioned was apparently already 5 times better than its baseline very early in training. So that shows the improvements aren't just coming from the non-recurrent parts, they're deeply embedded in those iterations, and that recurrent blocks thinking time. What's also fascinating is how it uses context. In OpenQA tasks where you provide relevant facts along with the question, the recurrent model significantly improves, almost closing the gap to Olmo 2. This suggests its capacity to reason about its context is pretty strong, even if it maybe has fewer facts memorized overall compared to larger models. And it also seems to use more recurrence, more thinking steps to extract more information when you give it additional few-shot examples. Though it does saturate eventually if you provide a lot of context, like with 2550 examples on ARCC.
Right. So we've seen the impressive results, the really fascinating internal workings. But where do we go from here? What are the biggest hurdles still, or maybe the most exciting next steps for this kind of architecture?
Yeah, it's definitely still a proof of concept, albeit a very promising one. Future work will absolutely focus on optimizing the training schedules, the data mixes, maybe architectural tweaks to unlock even more potential. But thinking about the broader implications, that smaller parameter count of these compute-heavy models, that could have broader benefits for the local deployment with commodity chips, making really advanced reasoning AI potentially more accessible, outside massive data centers.
That would be huge.
Absolutely. And there's also this really fascinating potential complementarity with mixture of expert or MOVI models. See, the recurrent depth setup seems to excel at learning these reasoning patterns, the how to think part, while MOVI models are really great at effectively storing and retrieving vast amounts of complex information. So this suggests a future architecture might actually combine both. Imagine a recurrent MOE model that refines its latent state over multiple iterations and maybe even routes to the same expert multiple times within a single thought process.
Wow, a model that can both think deeply and pull up specific facts efficiently.
Exactly. That could be incredibly powerful. But there's always a trade-off, isn't there? While this latent reasoning is powerful and it captures aspects of thought that might defy verbalization, it also comes with costs in model oversight. It's harder to follow compared to those verbalized chains of thought, which are, currently still human readable for the most part. So we gain this deep reasoning, but perhaps lose some of the immediate interpretability. It's something to keep in mind as we push these boundaries.
That's a really important point to consider. So as you, our listener, go out your day, maybe think about this. If AI is beginning to learn to reason in ways we can't quite articulate, maybe ways that don't even map neatly onto human language, what does that mean for how we understand intelligence itself? What fascinating, potentially nonverbal computations are happening just beneath the surface of the next answer you get from an AI?